Good afternoon, ladies and gentlemen, and welcome to another webinar here at the National Library of Scotland. My name is Kenny Redpath and I'm the Events Officer at the Library. It's my pleasure this afternoon to introduce Martin Disley, who's here to give a talk called Art and AI, Mapping Imaginary Worlds. Martin is a sound and new media artist based in Edinburgh. His work has been exhibited at the V&A Museum, Summer Hall and Hidden Door Festival, as well as locations across Europe and beyond. He is currently artist in residence at the National Library of Scotland, where he is using machine learning techniques with the collections. This work has been supported by the Creative Informatics AHRC funded project at the University of Edinburgh. So without further ado, hopefully over to you, Martin.
All right, thanks for that, Kenny. I'll just share my screen. You can get started. Okay, thank you all for tuning into this. And I wanted to first start by thanking the NLS for having me, bringing me on board to work on this project. I want to thank Sarah Ames and Chris Fleet especially for their time, enthusiasm and support over the course of this. So as Kenny said, I'm here under the dual guise of the NLS Arts in Residence and the Creative Informatics Resident Entrepreneur. So Creative Informatics is a AHRC funded research and development program for promoting data-driven technologies in the creative industries. The Resident Entrepreneur Program funds individuals and teams for up to 9 months in order to develop a new product or service within or alongside a host organization. So I applied for this program and I was lucky enough to be accepted and then paired up with the NLS. My proposal sought to address the problem of exhibiting large collections by leveraging generative machine learning and artistic practice. Cultural institutions such as libraries, museums and galleries are increasingly engaging in digital archival and often seeking to utilize these digital assets through exhibition. However, the pressures of the attention economy present a challenge to increased engagement. How can these institutions attract new audiences with vast collections that when these collections are presented at scale are often perceptually overwhelming? So my proposal sought to address this challenge by developing new bespoke artistic data visualization service. The works produced from this process aim not only to unlock hidden value within these collections, but also allow these institutions to communicate this latent information through new modalities of experience. And through framing this project as an artist in residence program, it allows myself as an artist to engage with the collections with more agency than perhaps if it was framed as a more specific design or purely technological solution. So first I'll talk a little bit about my background and I'll highlight a few projects that I've worked on that cover the breadth of the media I work in. I'd like to mention a couple of artists that, and their works that have really linked my previous work to the practice I've engaged in throughout this project. And following that, I'll take a look at the technology that I've been using and try and give an overview of how that works. And then finally, I'll let you see some results. So my background is in music. I studied music technology at the University of Edinburgh and then went on to a program called Sound and Music Computing at the University of Pompeu in Barcelona. And I've worked as a composer and a sound artist on several projects since graduating. For the project shown on screen, myself and about 10 other composers who make experimental electronic music were asked to contribute to a rescoring of the Die Hard soundtrack for an exhibition in Ghent, Belgium. This was subsequently released by the Italian record label Rest Now. Another project I've worked on, which came about through a collaborative commission from the MUBA Museum in Barcelona, where I was living and studying at the time, and the Bauhaus Museum in Weimar. A group of artists from each city were asked to create audiovisual works that linked areas of the city, each city, to the fascism that each nation had endured during the 20th century. I chose to examine the Plaza de Saint-Philippe Neri, which was bombed on the 30th of January 1938 during the Spanish Civil War, where some 42 people were killed, in this tragedy, most of them child refugees who were taking shelter in the basement of a church. The aerial bombardment left this pockmarked scarring that wraps its way entirely around the square. And to add insult to injury, the Francoist authorities, after the city fell, circulated the myth that this pockmarked scarring was the result of anarchist executions of church priests. And unfortunately, this myth has some staying power, as it seems to be given to, you can quite often hear it being given to tourists from tour guides around the city. So to contribute in some way to a truthful retelling of this tragedy, I've attempted something I've recently started calling forensic composition. I took the panoramic photo of the facade into Photoshop and manually traced out the damage on the walls. I was then able to convert this information into a machine-readable format called MIDI. And MIDI information, if you're not familiar, is a bit like it's a machine-readable music event information. So if we were to take the image on screen now, the left to right becomes the time axis, and the top to bottom becomes pitch information. I was then able to use this information to trigger synthesizers and sculpt a composition out of it. I then mapped this audio back onto the video in the form of a score reader, following the tracing along the wall and playing the holes in the wall, almost like a music box system. And I'll let you hear an excerpt of that now. Another project I've worked on that involved a technological remediation of some source material is a Twitter bot called the List Tweeted. A Twitter bot, if you're not familiar, is a bit of code that sits on a server and automatically composes and publishes tweets. This bot periodically generates tweets based on the entries from the list, a record compiled by the network United for Intercultural Action of every reported instance in which someone has died trying to migrate into Europe since 1997. What is initially striking about this list is its scale. The collective loss of life is profound. And other attempts to communicate this information visually, most seem to accurately capture this scale. But in looking at these visualizations, I was moved to consider what we lose when we focus too narrowly on representing this alone. This project attempts to retain that sense of scale without minimizing the tragedy each loss of life presents individually. The Twitter feed allows for scale to be represented temporally. The tweets come out every 4 hours, which would be about the interval between these deaths had they occurred periodically. It will take years to tweet the more than 34,000 entries of the list. And with scale represented on the temporal plane, each individual is afforded a more detailed acknowledgement. So I'd like to look at a couple of artists who've incorporated archival or archives into the practice in some way. The first artist I'd like to look at is an artist called Odell. and specifically a piece from 2015 called the Bureau of Suspended Objects. The Bureau of Suspended Objects was the result of Odell's residency at the San Francisco Recology, the dump. The residency allows artists daily access to the public disposal area, where unwanted objects are discarded and processed on their way to landfill. Odell used her time at the Recology to build an archive of the objects she found. In her words, activities of the BSO stem from the assumption that we are estranged even from those objects closest to us, or that their inner workings and past lives are too often experienced as opaque and inaccessible. As such, research at the BSO involves learning to read and understand an object on its own terms, to understand why and how it came into being. She has also written about her experience of archiving as something she calls observational eros. She writes, "The observational eros is the emotional fascination with one's subject that is so strong it overpowers the desire to create anything new." Another work I'd like to highlight is a piece by the artist and geographer Trevor Paglin. They took the faces from the accused and the dead, examines the National American Standards Institute database, whose archive of mugshots featuring those convicted and those merely accused once served as the predominant dataset for facial recognition technology. The Institute gave developers access to its database to train and test their algorithms. Facial recognition software was built from images of prisoners and has since been repurposed by the US government without their consent. The work criticizes this violation of privacy at the core of facial recognition technologies and the institutional bias perpetrated by this training data. The work deliberately invokes images of a phrenology database, establishing a haunting parallel between earlier and contemporary uses of photographic technology by bad actors. So this next bit is where I talk about the technology. And I'm going to assume that most people here are not particularly familiar with these kinds of technologies, but I am going to try and cover them in some depth, as I think it helps to unpack a bit what the work I've been doing, and also part of my practice has become about demystifying some of these processes. So on the left here, we have an open source repository where the code that makes up the machine learning technology I've been using is hosted. It's freely available, although you can't just run it on a laptop or a normal commercial desktop. You need access to high performance computing resources, either via a server or with a custom built machine. And on the right, you see a demo of these results in action. This is called StyleGAN. The faces you see on the right-hand side are not real. These people do not exist. StyleGAN is a kind of architecture called a generative adversarial network, GAN for short. This is an algorithm that, given a data set of images, will attempt to create new instances or fakes of that data set. In the demo you see here, the architecture has been trained on the FFHQ dataset, a dataset compiled of 80,000 portraits scraped from Flickr. That's without the consent of the account holder or the person featured in the photo. Of course, it wasn't long before artists got their hands on this technology. The example that's got the most media attention, but is by no means a pioneering example, was the work of the collective Obvious, who printed out the output of their network onto canvas and sold it at Christie's for over because they controversially used code without amendment written by an artist called Robbie Barat. This opened a real can of worms with regard to the provenance and legal attribution of works of this nature, which was this time played out quite publicly on Twitter. And that's a really interesting conversation within itself, but it merits entirely its own presentation. So by now you're probably asking what on earth this GAN thing is anyway. And GANs in their simplest form are two deep neural network architectures, and I'll go into what those are in a second, that work in apparent opposition to one another. So on the left-hand side of the screen, you have one network called the generator, and to the right of it you have one called the discriminator. The generator generates new instances of data, while the discriminator evaluates them for authenticity. i.e. the discriminator decides whether or not each instance of data that has been fed by the generator belongs to the dataset it has been trained on or does not. The repetition of this feedback loop between the two competing networks results in the generation of new data instances whose features correspond and mimic generalized or stylistic trends within the dataset. In other words, the process becomes an arms race between the generator and the discriminator in understanding what's visually consistent within the dataset. So what is a neural network? It's easiest to imagine a neural network as a series of stacked layers, with each layer comprising of something we call nodes, and these nodes just contain a number. Every node is connected to every other node on its neighboring layers, and that connection, that relationship, is also defined by a number. In the example on screen, we're trying to train a network to understand handwritten digits. These digits are presented to the network in the form of an image that's 28 by 28 pixels. This is a black and white image, so a pixel is just a single number between 0 and 1. So if we string all those pixels all the pixel data into one long string, you have a string of numbers that's 784 long. And we call each of those numbers activations. And the closer the number is to 1, the brighter the activation appears in the diagram on screen. So the pattern of activations causes, at the input layer, causes some very specific pattern in the next layer, which causes a pattern in the one after it, which finally gives us a pattern at the output layer, and the brightest node, the node closest to the value of 1, represents the network's choice for what it thinks that digit is, so to speak. If they don't converge, or if they converge on the wrong node, which is likely to happen at the start, since the stage is basically just guessing, we can help the network understand in what way it is wrong. So if, for instance, the digit 7 goes into the network and it comes out as a 3, we know that we know that it was meant to be a 7 because the training set is labeled, and we have all these images labeled with the true digit in them. We know we can define what's called a cost function, and that's how we tell how wrong it is. So if we were to put a 6 into the network and it was to come out thinking it was an 8, we would understand that that was less wrong than a 7 coming out as a 3. Why? It's not because a 6 is numerically closer to 8 than 3 is to 7. It's because a 6 really kind of looks like an 8. And the network can push itself in the right direction because it always makes the smallest changes that are going to have the greatest effect. In this example, it learns that the top loop of a 6, if you connect that all the way around, you basically have an 8. So there's not much change in terms of pixel value to go between a 6 and an 8. There's certainly a lot less to change than to go between a 3 and a 7. So what do these activations mean, and what's actually happening in each layer? As I mentioned previously, the patterns of activation in each layer are formed through their relationship to their neighboring layers. Each layer in the network tries to learn something unique about the construction of the thing that they're trying to understand. In the example on screen, you can see that in the first layer, the network has understood the most basic building blocks of a digit. These are half lines, straight, angled, pointing in different directions. In the second layer, it's understood a slightly larger construction, like full lines and whole loops. And finally, using the activations of the output layer, the network has guessed that if there's a loop on the top and it's connected to a line-like shape extending downwards from the right-hand side, then that's probably a 9. These short animations come from a YouTube series called 3 Blue 1 Brown, and so the videos are really excellent. And if you're interested in this kind of thing, the series is about an hour long, and you will get, I promise you will get a really intuitive understanding of how these things work once you've seen that. So anyway, back to the GAN. So we know we have a discriminator and a generator. And as we know, they work against each other, one classifying images and one producing images. So feeding these networks on the right-hand side, you see we have this thing called a latent space, along with a bit of noise. And the latent space is quite difficult to get your head around at first, but you have to imagine it simply as like a three-dimensional cube filled with a bunch of evenly indexed points which we can sample from. Because in reality, it's actually a 1024 dimensional space that has no theoretical bounds, but that's a lot harder to conceptualize. So just picture this instead. Just an index space filled with points that we can sample from. So imagine we trained this network to understand chairs, and we'd fed it thousands and thousands of chairs of all different kinds. And now we're able to sample from this latent space to see what it's produced. But one of the most interesting things about these trained networks is we're actually able to visualize the movement between these sampled points. So on the left and the right, you have two chairs, 2 points in the latent space. And we can also view and visualize everything in between. This is more than simply crossfading or shifting between two images of chairs. At each point on this line, we're visualizing a new, unique chair. And we can infer something from this about what the network constitutes chairness. It thinks that chairs can have arms, but they might also not have arms. And it thinks the slats on the back can be vertical and can be horizontal. And somewhere in this network, not on this vector or this line that we're visualizing right now, there's every combination of those, what we call features. So you can see that we're able to build up these really complex representational models of phenomenon, and we're able to explore them in really interesting ways. So with access to this technology and the NLS's digitized collections, I had to decide what to work with. And I was immediately drawn to a couple of specific collections. The Thomas and Anne plates of Victorian Glasgow on the left there, and the Scottish Bridges collection. That's the fourth bridge in the Taybridge inquiry, along with the map collection in general. However, there are a few practical constraints that need to be considered when working with GANs. First of all, you need more than 1,000 images to produce the most realistic results. In the tens of thousands is actually preferable. And the images all need to be the same size and a square crop. So given these constraints, the library's map collection seemed like the most suitable candidate. I'm also I really love looking at maps, and so this decision wasn't born out of necessity at all. I'm forever getting sucked into something the artist James Bridle calls Street View Wanderlust, which is the voyeuristically and virtually exploring places that I've never been and places that I have. So anyway, this is the collection of Scottish Admiralty charts from 1795 to 1963, and this is where I started. As I mentioned above, there's a bunch of pre-processing that's required, and I was able to utilize this. These were such large images that I was essentially able to cut tiles the required size out of them. So I ended up with about 9,000 images of this data set, in this data set. And here are some of the results. These are the fake images that are produced by the network. It takes about a week of running this computer at full hilt to produce these results. So it makes this quite a deliberate practice. We're very accustomed to having the computer react so fast, and for it to wait for us to make the next move these days is quite different from a lot of other digital practice. As we saw with the chair example earlier, you're able to interpolate between the index points in this latent space. And I'll just let this play for a minute now. The models can actually be further manipulated if we really start to explore this latent space. By the nature of the architecture, those fakes which are technically more successful, i.e. they trick the discriminator into thinking they're real more often, they're clustered at the center of the latent space. But we can also start to explore the far reaches of the network as well, and the results get more and more abstract the further we go out from the center. I'm currently working on a solution to be able to manipulate this truncation parameter. This is the distance from the center that you're viewing from. I'm working on a solution to be able to manipulate this in per frame so that I can transition smoothly from those realistic results we just saw to the more abstract ones here. Next, I looked at a collection of 6-inch to the mile OS maps from 1900 to 1925. This was a much larger collection, totaling over 20,000 images for this one. And again, here are some fakes for this one. And I'll just play an interpolation of this one. For technical lockdown and Google Drive related reasons, the training set was actually capped at 20,000. This was a much larger data set, and it could have been 2 or 3 times that amount. But for some reason, the subsets of maps that I ended up with seemed to be focused very heavily in the northeast of England, and a lot of them had the original LNER railway running through them. And through some sort of quirk of the network and I guess the infrastructure of that time, the network produces or thinks that lots and lots of things are railways, far more railways than roads appear. And it's almost like an inverse beaching report, where every town has about 2 railways coming through it. And finally, I looked at a collection of geological surveys from the 1840s to the 1940s. This is the smallest data set I worked with, about 800 images in total. And again, here are the fakes from this run. These results aren't cherry-picked at all, and you can see the effects of having a smaller data set here. The model, in machine learning parlance, we say that the model hasn't generalized very well. But in other words, that means that there's just a lot less variety. Essentially, it's learned here that if it produces almost an empty canvas, that it can, it can fool the discriminator that way. So as I delved more deeply into thinking about maps and thinking about maps specifically as a technology, I was reminded of the work of Kurt van Mensvert. His pyramid of technology describes the 7 levels at which technology may function in our lives. The pyramid is inspired by Maslow's hierarchy of needs. And similarly to Maslow's model, technologies move up through the various levels of the pyramid as lower stages are fulfilled. The 7 stages show how technology can go from an idea to something that is so accepted that we view it as vital or even natural. And we don't really think about maps as a technology, and they probably sit somewhere between vital and invisible on Mensvert's pyramid. StyleGAN, on the other hand, is a great example of an operational technology. I can use it as I have access to computing resources and I can read code, but it's not really accessible or broadly applied. I find it really interesting that as technologies move up the pyramid, they tend to shield themselves from critique. We have a language and a discourse for critiquing technology, but that is lost on anything that escapes such a categorization. Maps, like AI, like StyleGAN, share in common the potential to advance any combination of insight and lies. They both construct reality as much as they represent it. The world has been reified in the image of the cartographer's vision as maps have been used as instruments of power. It's a form of representation which facilitates domination and control through obscuring contested histories about the physical world. The morphing textures of the videos I've generated expose the ability of the maps to encode these lies. As we saw earlier, the GAN takes visual noise as its input and produces convincing fakes as its output. This reveals that if noise can be rendered coherent, the maps are legible and grammatically consistent. You can look at the maps produced by the AI and imagine what that space might look like in your head. So if noise can be rendered legible, then anything can. And I would argue that this is evidence and a reminder that maps are far from objective renderings. And with that, I'd like to play the final video of the triptych of models I've made as I close. Thank you very much.